Good morning, ladies and gentlemen. I would like to warmly thank the organizers of the BBEST conference that they have invited me to present the work we are carrying out in the frame of the Becool project. And more specifically, I would like to thank Professor Antonio Bonomi for all his kind collaboration on that. So I am Myrsini Christou. I'm leading the Biomass department of CRES, Center for Renewable Energy Sources and Saving in Greece. And I would like to present you the work we are doing on biomass production and feedstock diversification for advanced biofuels in the frame of the Becool project, that it is a Brazil-EU collaboration for development of advanced lignocellulosic biofuels. So this work is due to the contribution of my colleagues at the CRES, University of Bologna in Italy, CNPEM in Spain, and CREA in Italy. A few words about the project Becool. As I said, it is a collaboration between Europe and Brazil. It started in June 2017 and will end up next year, 31st of May 2022. It is a consortium of 12 partners from 7 European countries with a budget of almost 5 million euros. And the project is coordinated by the University of Bologna, Professor Andrea Monti. In this project, we are developing value chains, process routes towards advanced biofuels, including aviation fuels. So the work we are doing in the Becool covers biomass production, logistics, the processing technologies, and all that is integrated into a market and value chain sustainability assessment. And of course, we have a specific work package on dissemination and communication results. And this is why I am here now presenting the results we have from the first part, from the biomass production part. So the objectives of this work is to increase lignocellulosic biomass production and to increase feedstock diversification without reducing food crop land. And this issue of not reducing food crop land is of specific importance for Europe, because this is the only way to include energy cropping and for energy production for biofuels, advanced biofuels production. So this work is first a review of the available biomass streams, available agricultural, forest and industrial lignocellulosic residues of potential interest for advanced biofuels in Europe and in Brazil. On innovative crop rotations, where we integrate non-food crops with food crops without reducing the food crop land, as I said before, and the cultivation of perennial dedicated lignocellulosic crops that could be grown and are grown in our experiments in marginal lands. So from literature review carried out, we have seen assessments of this residual stream, the majority of which are agricultural residues the majority of the agricultural residues is mainly straw. So there is a wide variation of assessments of the availability of biomass, starting from 130 tons, million tons of dry matter per year, adding up to almost 500 million tons of dry matter per year by 2020, which could go further on for 2030 and could reach 286 up to 500 and more million tons of dry matter in 2050. As you see in the presentation in the graph on my right-hand side, the green part of the bars is the straw, so the majority of agricultural residues throughout Europe is mainly straw. And this is from the S2Biome project assessment. And in the countries that are involved in the biomass production in the Becool project, that is Greece, Italy, and Spain, we have seen that again, straw residues is the dominating agricultural residue. And that accounts up to 85.3 million tons of dry matter, 87% agricultural. Going to the technical potential for energy crops, there are also assessments that how this develops to 2030, and according to the assessment, at the minimum of almost 200 million tons of dry matter could be produced by energy crops in 2030. That could be even higher, even reaching 1 billion tons with the best scenarios, the most optimistic scenarios. We selected these three areas, three countries in Europe to grow biomass in the Becool project, Greece, Italy, and Spain, because they have almost similar characteristics with the Brazilian climates, and because those three have differences in terms of their average daily temperatures, a bit higher in Greece, a bit lower in Italy, differences in the cumulative global radiation and in precipitation, where we see that the Italian conditions are more rich in precipitation, while in Greece and Italy we have more arid conditions. I talk about the crop rotations, why we have selected crop rotations. First, because the 2/3 of the arable land in Europe is dominated by conventional crop rotations, wheat and maize. So the concept here is to introduce alternative crops that could produce energy and also not affect the food cropping lands, as I said before. Why crop rotations in general? It is because they can assure enhanced soil fertility and higher yields, improved soil structure, and maintenance of long-term productivity and organic matter, because they have longer periods of land cover. So they have a lower erosion. They protect the soil from erosion. Then there are reduced use of agricultural inputs such as agrochemicals and synthetic fertilizers if legumes are included in the crop rotations. There is also greater market opportunities because more than one crop is involved in the crop rotations, so that end up to different markets. So the crop rotation lowers the economic and climatic risks. Increased biodiversity, of course, less monotony of the landscape, and time-diluted farming activities, since the agricultural equipment can be used for a variety of crops. The disadvantages is that there is a higher level of farm organization and farmer skills requested, and there's need for diversified agricultural equipment and agricultural supplies if the crops have to be dealt differently. Reduced land availability for the most profitable crop, of course, sometimes unfamiliarity of farmers with the crop rotations, and a very interesting, very crucial disadvantage is that the fact that since the farmer has to keep the scheduled crop sequences, then he has no choices to select crops every year. He has to follow the strict program. The crops that we have selected for the crop rotations are biomass, so fiber sorghum, hemp, kenaf, and sun hemp. They are all annual crops, spring crops, and they were selected because we have tested them before, and we saw that they have modest requirements in irrigation, fertilizers, and they have they are adaptable in a range of climate conditions and soil conditions, and they produced good yields. Especially fiber sorghum is grown he's tested in also in the Brazilian conditions in the frame of the sweet fuel project. They have quite nice yields, up to 13 tons per hectare of dry matter for sorghum, 8 tons per hectare for hemp, and also kenaf is tested, and we saw it has yields of 10 to 20 to 15 tons per hectare of dry matter in several experimental fields in South Europe. Especially hemp can be absorbs heavy metals, so it can be used for remediation of contaminated soils. And sun hemp as a legume, through the biological and nitrogen fixation, it can improve soil fertility. The crop rotations that we have tested is a traditional one: maize, wheat, maize, and wheat. And then the rotations from 1 to 4, when the alternative crops, I said before, sun hemp, fiber sorghum, kenaf, and hemp are introduced before wheat. And then after wheat, there's some hemp in all rotations. And then, of course, follows maize and all these crops again, and then finally wheat, and on and on. The last rotation, the R5, includes sun hemp and wheat every year. So according to the first 3-year rotation cycle, in Italy, Greece, and Spain, Italy in red color tiles, and Greece in blue, and Spain in green, we have seen that the wheat grain yields are not affected. The wheat yields are not affected by the previous crops. However, the biomass yields are affected, and actually they are multiplied. They are much higher after in the rotations where the alternative crops are included. And we have seen that the rotation R2 and R3, that is the introduction of fiber sorghum in the rotation, and kenaf makes a difference and actually assures higher biomass yields. The lowest biomass yields were recorded in the conventional maize, fallow, and wheat rotation. And going to each country specifically, we have seen that in Greece and in Italy, the highest biomass yields were achieved because of the inclusion of fiber sorghum, while in the case of Spain, highest yields were achieved with the introduction of kenaf. So biomass yields reached even 80 tons per hectare of dry matter. In Greece, up to 50 tons per hectare of dry matter in Italy, and up to 30 tons per hectare in Spain. However, we have to take into account that this is experimental fields, so yields could be higher. Why we have selected perennials? Because they can grow on marginal lands under biophysical constraints, lands where the food or feed production is economically non-feasible. Thus, they cannot compete with food crops on the lands. They have low input requirements. They have 10 to 25 years of productive life, very good yielding potential under those constraints. And they offer not only energy resource, but they could also offer soil protection, landscape improvement, and so on. The perennial grasses we have selected is giant reed, miscanthus, switchgrass, and tallwood grass. The first 3 are perennial rhizomatous grasses, all very well grown in the Mediterranean basin, but also throughout Europe. Especially giant reed and miscanthus are propagated with rhizomes, so they have relatively high biomass production cost because of the establishment with rhizomes, whereas switchgrass can be sown, so it is biomass production cost is much lower. They are all fully mechanized. The production is fully mechanized. And they are all low input crops and highly productive, considering, of course, the arid areas that they are grown. The yields are up to 20 to 30 tons per hectare of dry matter for giant reed and miscanthus. Switchgrass follows from 80 to 25 tons per hectare, while tall wheatgrass is a perennial grass of minor importance, mainly grown as a forage crop, but it is very good crop for saline soils. It is alkali tolerant cultivated crop, so it can reduce salinity from the soils. So according to our trials, I have to say the yields that we have found from literature are depicted and are shown. So in Italy, we see that biomass yields of giant reed after 13 years of cultivation, they are reaching 20 tons per hectare, while with switchgrass, it could be 15 tons per hectare. In Spain, switchgrass also had higher yields of 20 tons per hectare, but after 7 years of growth, it reaches a little less than 15 tons per hectare, while tall wheatgrass is a very low productive perennial grass. In Greece, giant reed and switchgrass grown in marginal lands. They have shown yields that started from almost 23 tons per hectare for giant reed in the first years of establishment, but then they gradually fall down and reaching little less than 10 tons per hectare after 16 years of growth. Likewise, switchgrass had the highest yields of 20 tons per hectare in the first year, but later on it more or less reached and stabilized at 10 tons per hectare per year. So some conclusions of the work going on is that biomass resource estimations are diverse, as you have seen, and sometimes contradictory, because the final targets, the models, the assumptions used for in each literature reference are diversified. But in all studies, it seems that straw is the dominating agricultural residue. However, we believe that optimized logistics could significantly increase the energy exploitation of more residual biomass types, like the prunings, for instance. Energy crops do have a significant role to play in increasing the biomass feedstocks, and they could be able to cover the high biomass yields. However, the strict sustainability constraints that exist nowadays in Europe, and the stricter they go in the future, might hinder their fast development. And it was interesting to see that the stricter the sustainability constraints are, then the higher share of perennial energy crops will be compared to annual crops, of course. So annual crop rotations, in at least our crop rotation cycles that we have tested, did not affect the grain yields, but they did significantly increase the biomass yields, which was a very good thing, very interesting thing to see. And the perennial crops show the wide range of yields from 88 tons to 15 tons per hectare. Okay, of dry matter, sometimes higher, depending, of course, on the climate, soil quality, if they grow in fertile or arid lands, cultivation conditions, if they are rain-fed, if there are nitrogen applications on those, and depending, of course, on the years of the plantation, since we are talking about more than 10 years of plantations. Many thanks for your attention. And if you would like to find more information, please feel free to visit our website and also our Twitter. And for more information, you could also contact me directly. Very many thank you and have a nice day. Bye.
Hello everyone. I would like to introduce myself in the beginning of this presentation. I am Mateus Chagas from the Brazilian Biorenewables National Laboratory, part of the Brazilian Center for Research in Energy and Materials located in Campinas, Brazil. And today I will talk about the design and assessment of optimal logistic chains in the context of BioValue project. This project involves 11 research institutions in Brazil, and I'm the coordinator of one of its work packages, the work package related with the integrated market and value chains and sustainability assessment. So let's start. Starting with the BioValley goals, the main objective of the project is the cooperation between Brazil and Europe for the development of advanced lignocellulosic biofuels, with the collection of literature data, lab and pilot plant scale data for technical, economic and environmental assessment of different biomass production systems and biorefinery configuration for advanced biofuels. The project is divided into 7 work packages, 5 of them related to the technical aspects of the project. In the first work package, the biomass production systems are studied, while the second work package deals with the logistic chains involved in the raw value chains. The third and fourth work packages deals respectively with the thermochemical and biochemical conversion routes to convert biomass into advanced biofuels. And finally, the work package 5, the integrated sustainability assessment of the different technical configuration of the projects are studied. The main objective of the integrated market value chain and sustainability assessment activity is to identify, through integrated sustainability assessments, the most promising value chains for the production and use of advanced biofuels in Brazil, especially sustainable aviation fuels. By quantifying the availability of currently produced biomass options in the country, here we are talking about sugarcane straw, eucalyptus and pine residues. And more than that, we want to establish plausible scenarios for the potential expansion of biomass production. And here we add also the energy cane as an option for biomass. And for that expansion, we need to consider reasonable assumptions, for example, for land use restrictions and future demand for aviation fuels. We want also to estimate transportation distance from field to conversion facilities, between conversion facilities, and finally between the conversion facilities to the main airports in the country. And finally, the last objective of this task is to perform a special logistic analysis considering the biojet fuel demand for the 3 major airport hubs in the country. In this figure, you can see the technical integration of the technologies involved in the BioValue project, considering the different biomasses which are converted even through thermochemical or biochemical conversion routes to intermediate streams like cell lignin, second generation lignin, or pyrolysis or hydrothermal liquefaction bio-oils. Those intermediate streams can be processed in large scale facilities like the gasification plants to produce advanced liquid biofuels. The main focus of the project is the aviation biofuels, but also green diesel, green gasoline, biomethane can also be produced through thermochemical and biochemical conversion routes. We start the activities of the integrated assessment by compiling plausible value chains, taking into account different alternatives for biomasses, which are produced in work package 1, the logistic chains and production potentials for different Brazilian regions, which are studied in work package 2, and finally biochemical and or thermochemical conversion routes for the production of the advanced biofuels studied in work packages 3 and 4. Considering all the technological alternatives studied in the project for both biomasses and conversion process, 76 scenarios representing plausible value chains were defined. And here we can see that those scenarios cover biochemical, thermochemical, and integrated biochemical and thermochemical industrial routes, and also cover the set of biomass defined for the project. In addition to the value chains defined for the Brazilian case, we will also consider an integrated Brazilian and European value chain, where part of the process occurs in Brazil and part occurs in Europe. For example, we could consider the production of biomass occurring here in Brazil and the densified biomass or fast pyrolysis bio-oil being exported to Europe to be used there to produce biofuels in that continent, or we could consider the whole chain to produce biofuels here in Brazil and the final fuels being exported to be used in the European market. Here in this integrated assessment, the teams of both products, the BioValue in the Brazilian case and the Becool in European case, will be acting together to get the results. To perform the integrated sustainability assessment in BioValue project, we will use the virtual sugarcane biorefinery framework. This framework has been developed by the Brazilian Biorenewables National Laboratory team and integrate computational models for the biomass production, industrial conversion, and final use of the products to calculate the sustainability impacts in environmental, economic, and social aspects. This framework can be used to compare different biorefinery alternatives to assess the stage of the development of new technologies and also to optimize impacts and concepts involved in the biorefinery concept. Perform the integrated sustainability assessment in the virtual sugarcane biorefinery. We start by the conceptual design of value chains where we define the process and how they are integrated in the value chain. Then we need to set the parameters and assumptions that will be used in the simulations and in the construction of the models used to calculate the technical, economic, and environmental impacts in the different value chains that can be considered. Setting the parameters, we can then represent the agricultural production systems in the Canasoft model and the industrial conversion facilities in Aspen Plus simulation tool. With technical results coming from the agricultural and industrial models in the virtual biorefinery, we can then use the results to estimate economic and environmental impacts related to the different biorefinery scenarios. We are using harmonized data and methodologies in the virtual sugarcane biorefinery to perform the sustainability assessment, starting with the technical assessment using Canasoft and Aspen Plus model, as I just said. Those models will give us the results needed to perform the economic assessments through the estimates of investments, the cash flow analysis, calculation of production costs, and so on. And also the technical assessment gives us the results to perform the environmental assessment using the life cycle assessment methodologies, using international databases for the life cycle inventories, and calculating different impacts in different environmental categories. And finally, the economic and environmental assessment results will be used to provide information for logistics and market assessments. Finally, to perform the logistics assessment, we will consider georeferenced agroclimatic data, which will be used in a crop assessment tool to estimate biomass productivity for each geographic point. That information will be then used to perform the integrated assessment in the virtual biorefinery, creating a georeferenced map for the technical, economic, and life cycle results calculated by the virtual biorefinery. The integrated framework will be then used to perform the logistics assessment in the project. Here we exemplify a logistic problem related to the biojet fuel in the Brazilian case. We will estimate the production cost and greenhouse gas emissions for each one of the points, considering the combination between biomass and the technological conversion routes. And then the integrated assessment will incorporate the cost and greenhouse gas emissions associated with the distribution of biojet fuels to the three main Brazilian airports, calculating then the impacts associated with the whole production and distribution and use chain. This was the general overview of the integrated assessments in the BioValley project. So I would like to thank you for your attention, and I would like also to thank IFAPESP for the financial support, and also the 4 Brazilian companies supporting the project: Embraer, Klabin, Petrobras, and Suzano.
Good afternoon, everybody. My name is Bert van der Beld from BGG Biomass Technology Group from the Netherlands. And today's presentation is about fast pyrolysis activities in the Becool project. And in fact, it is a joint effort of BGG and VGG from Finland. First, I will briefly explain the role of fast pyrolysis in the Becool concepts and then continue with pyrolysis experiments performed by VGT. Then I will present the experimental work on pyrolysis oil gasification done at BTG and then end this presentation with a summary and some conclusions. First, the role of fast pyrolysis in the Becool projects. Within the project, fast pyrolysis is considered within 2 different concepts. The first approach is to replace the lignin combustor in a second generation ethanol plant by a fast pyrolysis process using the same lignin. And similar to combustion, the fast pyrolysis plant will also provide all the heat and electricity required by the ethanol plant, but instead of excess steam and electricity, a lignin oil will be obtained as a valuable byproduct. The second approach is to pyrolyze different types of biomass and then convert the resulting pyrolysis oil to syngas via gasification. Reasons to use pyrolysis oil as intermediates are that it can improve the logistics, and it has the advantage of decoupling of production and use in time, location and scale. Furthermore, it's easy to pressurize pyrolysis oil, which is an advantage for syngas production, and likely a catalyst can be used in the gasifier. The remainder of this presentation I will focus on this second route. And within Becool, several value chains are evaluated, and here you see the specific fast pyrolysis value chain. It starts with local biomass, which is transported to a regional fast pyrolysis plant producing the pyrolysis liquid. This is the decentralized part of the chain. The oil is then transported to a larger scale gasifier where pyrolysis oil is converted into syngas, and subsequently the syngas is converted to the desired chemical or fuel, like for example methanol or physiotropes. Within Becool, the production of physiotropes is considered in the models. Here you see an overview of the biomasses selected and tested in Becool. We have arundo, sorghum, eucalyptus and bagasse. Due to some issues with the conversion of the first batch, sorghum has been tested twice. Well, clear difference can be observed in the S content of the different biomasses, as well as the chloride and sulfur content. Bagasse is used as a common feedstock in both the Brazilian and the European projects, so both in BioValue and in Becool. And these feedstocks have been supplied to VTT for the pyrolysis experiments. Here you see a schematic drawing of the setup of VTT for small-scale, bench-scale fast pyrolysis experiments. It is based on a bubbling fluidized bed pyrolyzer. The capacity is 1 kilogram of biomass per hour, and they are typically operating at 480 degrees C, and they use nitrogen as fluidizing agent. Biomass is fed to the reactor and vapor is generated. After the reactor cyclone is installed to remove the char, then a condensation train to collect the liquids, and the remaining are the non-condensable gases. The results of their experiments are summarized in this table. Arundo and sorghum led to an organic yield of around 40%, eucalyptus of around 51%, and bagasse even above 60%. And this also corresponds with a reverse observation for the water content. Bagasse gives the lowest value, arundo, sorghum the highest value. Also chloride and sulfur content is the lowest in bagasse, which is an advantage for use in any catalytic downstream process. So in fact bagasse gives the best performance. The only drawback what we see here is the relative high viscosity, which may be a challenge for proper atomization. All these pyrolysis oils were sent by VTT to BTG for the gasification experiments. And here you see a schematic drawing of the setup used by BTG. It represents a kind of autothermal catalytic gasifier, although the partial oxidation and the catalytic reform are installed in separate units. The capacity is 2 to 3 kg of pyrolysis oil per hour. We use pure oxygen for the oxidation, and we add some steam. The catalyst we are using at the moment is a standard nickel alumina reforming catalyst. It's a commercial catalyst, and so far in all the testing we only used one catalytic bed. In principle, after the first bed we can install a second catalytic bed, and at the end the syngas is cooled and analyzed. Here you see also a photo of this setup. At the left bottom you can see the pyrolysis oil feeding system. Above that is steam generator, and on the left the gas cooling. And at the back, which is a little hard to see, we have the gasifier and the catalytic bed. So the different oils received have been gasified, except the bagasse oil. That one was received quite recently, and the test has not yet been carried out, but will be done in the coming months. Also in this case, pyrolysis oil from pine wood was added for reference, but it was not selected in Becool, but just as a reference oil. And I must say, in all cases, we added 28% of ethanol to enable proper atomization on this small scale. And in the figure, the concentrations of the main gas components, these are hydrogen, carbon monoxide, carbon dioxide, and methane, are shown for the different process oils. In all cases, the hydrogen content is nearly constant and around 50, just above 50% by volume. Some differences are observed in CO and CO2, which is caused by difference in the ratio between fuel and the required oxygen to achieve a certain gasification temperature. And normally a lower energy content of the fuel requires some more oxygen, and it would result in some more CO2 produced in the gasifier. If you look at overall results of the gasification, it's summarized in this table. Well, I must say it's always a challenge to have very accurate mass balances in small scale units. Anyhow, the carbon to gas is in all cases above 90%, which is quite good, but could be further improved, and we are working on that. The cold gas efficiency is typically in the range of 75 to 85%, and probably the 89% of sorghum might be an outlier, probably due to some experimental inaccuracies. For tar, in our experimental work for tar, we only use the SPA method, and in all cases the concentration was well below 10 milligram per cubic meter, which is quite low. The hydrogen over CO ratio is above 2, which is also due to the use of the nickel reforming catalyst. The stoichiometric number is on the low side due to the presence of significant amounts of CO2. And in fact, to increase the stoichiometric number, which can be relevant, for instance, for methanol synthesis, the CO2 should be removed from the gas. We can also summarize in this graph, we can summarize the results in this graph. What we plotted here is on the x-axis the lower heating value of the pyrolysis oil feedstock, including the ethanol. On the y-axis, the syngas yield, and the syngas yield is defined here as the total moles of hydrogen plus CO divided by the amount of fuel in kilograms. Besides the Becool pyrolysis oils, also the wood oil with different amounts of ethanol are plotted. And different amounts of ethanol means also a different heating value. Increasing ethanol means increasing the heating value. And what you see is a clear linear correlation between the heating value of the fuel and the amount of syngas produced. To summarize our work, VTT succeeded in converting the different biomass into fast pyrolysis oil. The best performance was achieved with bagasse. VTT succeeded in producing clean syngas from these oils, except bagasse derived oil that will be done in the next months. In all cases, we added 28% of ethanol to ensure this proper atomization on this small bench scale. And finally, the syngas yield nicely correlates with the heating value of the feed oil. And that brings me to the end of this presentation. Thank you for your attention.
Hello, my name is Ricardo Soares. I'm a full professor at Federal University of Uberlândia, and I will spend the next minutes with you talking about the thermochemical routes for advanced biofuels production activities, which are being conducted in BioValue Work Package 3, where I am the coordinating. I'm sorry in not updating this consumption evolution data, but it's not quite different from nowadays current one. It's observed that the kerosene and diesel oil consumption and their price have been increased along the last years, leading leading to a difference between the diesel consumption and its production, for example, and the way to solve this problem and also environment issues was stimulate biodiesel production. However, biodiesel production may suffer some drawbacks, such as poor storage stability, poor cold flow properties, low energy density. Its production process not totally green because you use methanol. Another solution is stimulate the use of electric or hybrid car, and the usage of electric hybrid car may decrease transportation fuel like ethanol, gasoline, and even diesel. And that way, the demand of these fuels will decrease in the future, maybe. However, the flight path to aviation green fuel not include electricity. It's impossible to use jet fuel, not jet fuel, but it's impossible to use electricity by aviation right now. So in the case of jet fuel, there is not still an equivalent green molecule such as FEM that can substitute or blend with traditional kerosene. Airlines company has set, for example, a target by 2030 to replace part of the fossil jet fuel by renewable one. For example, this target for 2050 try to reach 50% of blend. Then there is a growing interest in developing process for the conversion of fats and oils, and mainly lignocellulose biomass can be used. This conversion of fats and lignocellulose biomass into hydrocarbon fuels can serve as drop-in replacements for petroleum derivative fuels. So, therefore, biojet fuel may push biofuel production in the future. There are some routes to convert biomass to jet fuel with their sequential process steps. For example, you can see here, alcohol to fuel, we have steps from dehydration, oligomerization, hydrogenation. Oil to fuel, the oxygenation, hydroprocess in general. Gas to fuel, Bentley, gasification, Fischer-Tropsch, and hydroprocessing, right? Nowadays, the main process approved by STM for biojet production is the EFA, or hydroprocess of vegetable oils. However, it's important to develop the Fischer-Tropsch one because it develop or improve the Fischer-Tropsch one because it use any crops and different residues in order to attend the increased demand. Because you can see, for example, here you have in hydroprocessing you use vegetable oil. In this route you use ethanol. Only in the gasification Fischer-Tropsch you use any kind of crops and residues. So it's necessary to improve this route. That way you can mitigate, for example, the demand of the oil production. Probably you don't have enough vegetable oils around the world for this purpose. Well, for develop the Fischer-Tropsch by crops and its residues, you can see the whole map of Brazil around, the whole map. There are different crops and its residues plant areas in Brazil. In order to identify and choose in the best biojet, advanced biofuel production hotspots, it's crucial to analyze the feedstock supply and cost, conversion routes and plant scale, logistics barriers, and gas house emission gas. All right. Therefore, different thermochemical conversion process routes may be chosen, depending on the Brazil region, the biomass characteristics, the biomass, the biofuel demand. So we can choose available thermochemical process conversion routes by using combination of gasification, Fischer-Tropsch, pyrolysis, slow and intermediate pyrolysis, HTL, hydrothermal liquefaction. So we can combine different thermochemical routes, depend on the region of Brazil, the characteristics of the biomass, and the available plants. So these are the motivation that to elaborate and start the BioValue project, where the main goal is to explore the synergies between biomass production, diversification, and logistics of defined value chains for production of advanced biofuels, in special focus on aviation biofuels by thermochemical route, integrate with the biochemical one. Well, then a well-qualified team was formed, including 4 state research foundations, 4 big companies in Brazil, and several research institutions, university and technical institutions in Brazil to carry out this project. Let's take a look of the BioValue work package activities. We will process 5 crude biomass and 2 well-processed one from work package 4. In task 3, we will do set some biomass and advanced biofuel characterization, commission, and analytical methods characterizing the thermochemical products. We will gasify the biomass, follow the gas cleaning in order to adjusting the syngas for Fischer-Tropsch synthesis, where or after that, we intend to obtain advanced biofuels after that. We will also process the same biomass by fast pyrolysis, process the same biomass by using the fast pyrolysis in order to providing bio-oil and or bio-oil plus biochar slurry mud to the gasifier. We will also carry out modeling and sustainability assessment study in co-processing for producing advanced biofuels. We also evaluate the hydrodeoxygenate modeling, HDO modeling, and sustainability assessment study for direct advanced biofuel production and the integrated process with co-processing. Similar path and goals will be done by use HTL process in order to compare with the fast pyrolysis one. Let's talk about our pyrolysis process. It's an autothermal fast pyrolysis. We can process 10 to 30 kilograms an hour of dry biomass in a bubbling fluidized bed reactor and produce gas, biochar, and liquid fractionating in 3 parts: an aqueous one called extract acid, where we can obtain most of the hydrophilic compounds such as acetic acid and levoglucosan. Visco, the other 2 parts, visco black organic phase, we can have the visco black organic phase in 2 parts, light and have bio-oil, where most of the lignin fragments are, as I mentioned before, the pyrolysis bio-oil may be the pyrolysis bio-oil may be co-processed, upgraded to maritime fuel and other advanced biofuels, and sent to the gasifier to be gasified and to obtain the syngas. Okay. Finally, so here we have the HDO process for stabilization and for bio-oil updating or upgrading, to be assessed, to be modeling by using Aspen. We use Aspen for modeling the fast pyrolysis, the HDO of the fast pyrolysis produced, and also we use a model Aspen to model the co-process by using our bio-oil obtained in our fast pyrolysis. Let's talk about, finally, let's move to the gasification for Fischer-Tropsch. So we are going to gasify, we are gasifying the crude biomass, the 5 crude biomass, the bio-oil and bio-crude from pyrolysis or HEL. We produce the gas mixture, syngas-based gas mixture, and then the gas have to be cleaned by using unit operation and catalytic process in order to adjust the syngas. Sorry, to adjust the syngas for the Fischer-Tropsch. So here we have the syngas, a clean syngas, doing the Fischer-Tropsch, follow the hydro treatment or hydro processing to obtain the advanced biofuel, the naphtha, gasoline, kerosene, and diesel. In the last slide, I can share with you the idea of the Fischer-Tropsch and the preliminary results from the Fischer-Tropsch. Well, here we can see, for example, the Fischer-Tropsch together with the hydro process. Fischer-Tropsch, the main reactors, the fixed beds, the slurry bed. We have the main reactions, produce alkanes, and we have the side reaction, the shift reaction. We have the polymerization degree. We evaluate by using the understood flow rate distribution. The reaction condition that we are going to take a look for. The temperature range, maybe we are going to higher temperature, and the main catalyst. Here we have the main characteristic of the main feature of the hydro processing. An idea of the project in Fischer-Tropsch is use a unique reactor or a multifunctional or hybrid catalyst. So doing the same port, in one port, the Fischer-Tropsch and the hydro treatment, hydro processing. So in that way, we can obtain directly the main products, the gasoline, kerosene, and diesel, using the same temperature and pressure. Well, we have here the preliminary adjust Fischer-Tropsch catalyst test, where stable activity with 60% of CO conversion, and a product distribution between gasoline and kerosene were achieved, because the alpha is related to gasoline and kerosene range. So these are the preliminary results. I cannot say right now the catalyst and the condition, because we are trying to integrate the process. So I would like to acknowledge my team and share with you the facilities that we have to carry out this project and future projects. So thank you very much. And if you have any doubts, suggestions, discussions, feel free to get in touch. Thank you.